It's early morning on a farm. The sun just cleared the horizon, and its rays are hitting this sealed greenhouse. Inside, a heavy dose of fumigation gas is trapped, meant to clear out pests. As the temperature rapidly spikes, the pressure builds. The gas pushes hard against the rigid panes, vibrating the glass right to the edge of shattering. From our perspective, this looks like a complete mess. Heat, pressure, and the space inside the greenhouse seem to be fighting a disorganized, chaotic war against each other. But if we zoom in, past the vibrating glass and down to the atomic level, that chaos disappears. Down here, we find an invisible, highly predictable tug-of-war for space. Scoring this battle allows us to predict exactly what this gas, or any physical system, will do next. Before we untangle the moving parts of an unruly gas, we need to establish the baseline rules of matter by looking at atoms locked in a perfect stalemate, solid crystals. Nature is inherently lazy. When particles settle into a solid, they solve their spatial problems by packing themselves as efficiently as possible to eliminate empty gaps. The most basic way they arrange themselves is called the simple cubic formation. Here, the particles only sit at the 8 outer corners of a microscopic box, but nature prefers a tighter fit. By shifting slightly, a formation called body-centered cubic takes advantage of the empty space inside that box, cramming one extra sphere right into the dead center. The tightest packing method fills the remaining exterior gaps. This is the face-centered cubic arrangement, where extra spheres sit flat on all 6 faces of the box. It's a logistics problem. If you need to ship spherical grapefruits in square wooden crates, you have to stack them in a specific pattern to fit the most fruit in the tightest space. Atoms do the exact same thing. These structural boxes are called unit cells. Every corner and every gap is the physical consequence of particles seeking their most spatially efficient resting state. To see how this applies to an unruly gas, imagine pumping raw methane into a flexible biogas storage bag on a farm. Avogadro's basic rule describes what happens next. If you add more particles to a sealed environment, you get more physical impacts, more tiny punches, against the container walls. To prevent the internal pressure from spiking under all those new hits, the container adjusts. The constant collisions push the piston up, and the space expands. Adding more gas particles is distinct from raising the temperature. While heat excites the particles already inside, Avogadro's law deals with the introduction of new mass into the container. The amount of gas is directly linked to volume. Bringing more fighters into the ring requires a larger arena to hold them. But what happens when variables stop taking turns? As a weather balloon rises, external pressure drops, temperature drops, and the volume expands all at once. To track this multi-variable tug-of-war, we use a single master scorecard, the combined gas law. This equation balances pressure, volume, and temperature in one line. Here is a useful shortcut. If any of those variables sits out the fight, say the temperature remains constant, you can simply erase it from the equation. You don't need to memorize 3 isolated rules for gas behavior. Every gas law is a smaller fragment clipped out of this one master rule. Let's return to the greenhouse. The glass is vibrating and the pressure is rising, but now we can solve the problem without guessing. Left, starting pressures and temperatures. Right, the microscopic arena. Watch the particles. Rising pressure squishes the gas, but rising temperature makes them move faster, expanding outward. We plug numbers into our master scorecard, converting Celsius to Kelvin first to avoid an impossible negative volume. This math functions as a direct translation of physical motion. Mastering it allows you to read the invisible mechanics driving the physical universe.